Hello and welcome. My name is Lars Jäger and I'm standing on the premises where the team Dirt Torpedo, a team of very skilled students, is developing a new innovative approach for a tunnel boring machine. Did you know that Elon Musk and his boring company have called for a competition to beat the snail? Well, basically, they are aiming to make tunneling more cost-effective and faster. Out of 400 participants globally, the team Dirt Torpedo made it onto the final 12. Curious? Well, then let's go in and meet them. So now we are here at the team Dirt Torpedo in the garage, I would say. With me we have Robin. Robin.
Hi, nice to meet you.
Nice meeting you. So you are the IT and networking expert here in that student team.
Yes.
And you volunteered to guide us a little bit through your project and the interesting parts of it. So why don't you tell us a bit more about the project itself?
Yeah, well, thank you for visiting us here at FFT Fulda, where we are assembling our tunnel boring machine. So we're a team of 12 students from 3 different universities, from DHBW Mosbach, Ravensburg and the TU Darmstadt. And in 2020, Elon Musk has announced the Not a Boring competition, where the goal is to bore a 30-meter tunnel as fast and as precise as possible. We thought this would be an amazing challenge, so we decided to take part in. And luckily, from over 400 teams, which initially handed in their concepts, we were one of the 12 teams who succeeded. And we're now building our final tunnel boring machine. And we did this because transportation is becoming increasingly difficult in nowadays world. And if you bore tunnels, conventional techniques, they're either inflexible, they're expensive, or they are slow. So we decided to hopefully revolutionize transportation.
Very interesting. And if I understand correctly, from the tunnel machine that you are building, you are not looking at the full portfolio of going from like very large tunnels for
No,
cars,
certainly not.
but rather the utility tunnels, right?
Yes, exactly. So our tunnel boring machine has the advantage that it's small, it's very compact, and it's not built for large tunnels. It's really built for micro tunneling, but it's also, due to its small size, it's very flexible. So one unique point is that we can easily build like curved tunnels, which is something you cannot do with conventional techniques, or at least not as easily as we can do it.
Understand. So a torpedo that can actually go in curves.
Exactly.
Excellent.
You got it.
Shall we have a look on the machine itself?
Oh, yes, please.
Good. So Robin, this is the Dirt Torpedo.
Yes, it is.
So tell me a bit more about the ingredients here.
So let's start at the front. So what we have here in red is the boring head, which is removing the soil. And the tools you see on here, they are from street construction work. They are usually used to remove like tarmac. Down here we have the hole where the soil is removed by a suction excavator. So let's go to the back where we have our first unique point. So below those bellows, you have so-called steward platforms or hexapods. Hexapods are a special construction which allow you to turn into each direction you want. Like you can rotate and you can translate. So that allows us to go around curves. And it also allows to compensate if we have different layers of soil with different hardnesses, because we would drift to the side and we need to compensate for that. This is a very unique point. We don't know any other tunnel boring machine which has this.
And that helps you on the precision.
Yes,
right?
Definitely, because it allows for 6 degrees of freedom, so we can even compensate very small deviations without any issues.
Interesting.
So let's go a bit further to the back. So what we have here are the so-called pressure bellows. So those pressure bellows, they are inflated and then they grip into the surrounding soil, and that allows us to push forward. And in our tests, we could hold about 1 ton with one of those pressure bellows, so they definitely should be strong enough for what we're doing with them. Here we have the second steward platform, and behind it the second pressure bellow, and then the third steward platform. And now there is another unique point of our TBM, which is the so-called liner unit. So in the front, we remove the soil, and then at this point, we mold the tunnel as we go, which is also something that you don't see anywhere in the tunnel boring industry. And this works by pushing out concrete through these tubes. There are another 2 down there. And this is a Teflon-coated steel tube, so it makes a really smooth surface in the end. And here we can see another couple of things, like we have the so-called guidance boxes.
I see.
Which allow for precise navigation which is important because we want to be as precise as possible, and inertial navigation wouldn't be possible due to the strong vibrations from the entire TBM. And here we see the special concrete valves, which are also specially made for us, which regulate the concrete pressure, and are also something you wouldn't find on the market, at least not as sophisticated as we got them.
I see. So in principle, you are taking the soil there, bring it out with another tube?
Yes, exactly. So there will be a large tube, a very large tube going from the back right to the front of the TBM, which goes to a suction excavator on the outside, which removes the soil and excess concrete from the pressure regulation. So it's very easy to remove the soil from the TBM.
So the Dirt Torpedo is basically leaving a tunnel already made of concrete behind himself.
Exactly.
So, and when I wrap this up, basically you have a boring head that was copied or inspired from the transportation industry.
Yep.
Then you have a unique feature of flexibility with 3 sections where you can basically bend your Dirt Torpedo in order to adjust.
Exactly, yeah, we can go around obstacles or we can adjust to varying soil density or hardness. Exactly.
Excellent. Controlled by a laser guidance system.
Exactly.
And the real unique thing that fascinates me personally most is actually the pressure bellows that makes this whole thing act like an earthworm inspired by nature.
Yeah, that's a really interesting point. Also because it's new research. You won't find something like this in the industry. So it's a brand new, it's very experimental. And we hope it will work, as we hope.
Fantastic idea. So now if that Dirt Torpedo is down in the earth and for some reason connection get lost, what do you actually do?
Well, we make sure connection doesn't get lost. So what we do is we engineer the entire machine for redundancy and the entire network. So while the network infrastructure inside the TBM is also redundant, we also have redundant uplinks to the outside. So we have 4 completely independent fiber uplinks to the outside. So we don't have any issues with interference. And each of those fiber cables is able to control the TBM on its own without any issues. So we have enough redundancy, and the standard Ethernet technology had allowed us to very easily reach this redundancy without having to fiddle around with complex configurations, because it's just standard network with link aggregation.
That sounds very exciting. So Ethernet technology, that's actually also part of our area. Can we have a look at the network rack?
Yes, sure. It sounds like a good idea. Let's head over there.
Okay. So Robin, this is the brain of your whole network, right?
Yes, it is. It absolutely is.
So tell me, how does it work?
So we have different components in here. So we start with 4 industrial servers, which are engineered to withstand the high temperatures and dust in the desert. Those servers are the brain of the machine, basically. We have 4 servers. 3 of them are active, and 1 of them is a hot spare because it's very likely that 1 server will fail, even though they are very properly engineered. And then the network, which you could say is the nervous system of the TBM. So we have a network that is partitioned into different parts. So we start, what we have here is the internal part of the network. This is where the team computers will connect. This is where our Wi-Fi access point connects. Then we have the public network, which is physically separated from all the internal networks. And because the public network is it's really public. So what we want to do is visitors will be able to plug in their laptops into those switches and be able to view the progress of the machine in the web interface.
I see.
Then we have just a simple switch we call the IPMI switch, which is just for the management planes of the servers and switches. And on the top, which is difficult to see, we have the so-called core switches, which are the most important switches of the TBM. Those are high-end 56 gigabit switches, which provide high throughput and redundancy for all the servers and the other internal switches. So each of the servers, for the sake of redundancy, has 4 independent connections to the core switches, distributed to both core switches from 2 different network interfaces, so we can tolerate multiple component failure at once. And also the core switches, they are stacked and also have redundant uplink, So once again, everything is engineered for redundancy. And this continues on the software side. So not only our hardware is redundant, but also on the software side, we have a so-called cloud-native software stack, which is used like nowadays, providing large network services like Netflix or Amazon. They're all using like cloud-native software because it's easily scalable and it just tolerates component failure very easily. Because if you have large-scale networks, it's very likely that some components will fail at some point. So we decided to use this software stack, which perfectly integrates with our network infrastructure. And the software stack allows us to ditch the conventional approach to controlling machinery. We have a microservice-based approach with different services which have different tasks, like controlling the TBM as the kinematics module, or a different output module that translates commands into a CAN network for those computers, which will be put inside the TBM. And it just tolerates failure. So it automatically fades over without anything to do from us. So if one server fails, it automatically knows what to do, fails over, and everything is up and running within a couple of seconds or even less.
Fantastic. From your mouth, I have to say this sounds so easy. But still, I guess in this whole project, you probably had a couple of challenges. What was most challenging for you?
Well, one of the most difficult challenges was probably sourcing all the components. So the network components we have here, they're actually from the second-hand market. Mm-hmm. We were lucky because those network switches, they don't have too large requirements. We could just use switches from the second-hand market. But still, we've also had to search quite some time for them because sourcing components is very difficult at the minute. And we've had really large issues trying to source the switches inside the TBM. Because in opposite to the switches here, which are nice and outside the TBM and are cool and all that stuff, switches inside the TBM, we have vibration, we have a lot of heat, we have possibly water and dust. So we really needed to find some switches which can bear with that, which was really difficult. So we found some switches, but for example, one of our supplier wasn't able to supply. So it was really, the biggest challenge was really to find parts which are available. That was the single biggest issue we had.
So, and then how did it come to Moxa then in the end?
Well, from my previous experience with a couple of embedded projects and my consulting work, I knew that Moxa manufactures good stuff, and it was, well, maybe just give Moxa a call. And yeah, that's basically how we discovered you.
So you gave us a call. What's your experience then?
So it was very easy to get this done because first phone call, standard, first need to find the right person. But afterwards, it was like we had a couple of talks to explain the situation, what we're doing, and explain that we're under very, very high pressure because just time is running out. And then it was very easy because Moxa just said, well, guys, we understand your situation, so we're just going to send some switches to you. And we do the formalities all later, but we just we want to help you as fast as possible, and we understand. And we luckily have something available, so just sending this out, and let's speak about the details later. It was a very, very easy experience, and we are happy that we found Moxa as a partner.
Yeah, I think it was a pleasure also on our side. So, which Moxa equipment are you actually using now?
So we're using a couple of different Moxa components. So, for example, we're using the TN switches and the media converters, which we put into IP67 boxes. But what about I show you how they're actually put into the machine?
Yeah, great. Please show me.
Perfect.
So here we are now looking into the machine. So one of the elements has been removed, kindly.
Yeah, exactly.
And what do we see here?
So what we can see here is on the bottom we see the IMC media converters, which are an important part because they allow us to convert the copper networking from the switches to fiber networking. And one important part was that because they are not IP67, so we had to seal them in a box. So we needed an industrial temperature range, which they have, which is very easy. And they also have redundant power input, which makes it even more suitable for our tunnel boring machine because we also have redundant power. On the top, we see the most important network component inside the TBM, which is the actual Moxa switch. So as we can see here, there's very little space inside the machine. Like we have this large suction tube. There will be additional pipes and cables for electrical signals, pressured air, water. And we had to mount them on the top here. So I'm just going to take this out. So we just managed to get a position where we can easily take it out. And we have all the cables on the other side, which is very convenient. So we can take it out if we manage to lose those screws. But yeah, it's very compact. It has a high temperature range. It's suitable for very strong vibrations, so exactly what we need. And it's very small. Like I was genuinely surprised when we received the package, when I saw those switches, because I expected them to be like twice the size or 1/2 the size. So I was genuinely surprised, pleasantly surprised how small they are. And another thing that really makes it easy for us is their wide voltage range, because we didn't know whether we will have 24 volts or 48 volts, and we can use those switches with everything from 24 to 110 volt DC, so it's perfect for our purpose.
So for the audience, it's probably relevant to understand. Here's the pipe where all the soil goes through, but still there's so much dust created and other dirt that still goes through in the ingredients here of the tunnel boring machine.
Yeah, exactly. Because we are sucking out air at the front, air needs to go in from the back, from outside the tunnel, and because we are in the desert, we will inevitably have lots of dust in the machine, and also because the tube in the front is not perfectly sealed, well, at least we assume, and maybe we have like a bursting water pipe or pressured air or whatever. So we really need an IP67 switch, because we don't want the switch to fail because the water pipe bursted. That would be a bad thing.
Mm-hmm. Our switch also comes with PoE. I think you are using the PoE functions as well, right?
Yes, we almost all PoE ports, so almost all of the 8 ports are used for PoE, because we have a lot of cameras inside the TBM. We also have some Moxa cameras, which you can see here, which are, well, kind of special industry cameras, because an IP67 camera, where you can actually turn the lens, the entire camera, is not something you see too often, but it's very useful for us, because we have those complex steward platforms, which are kind of experimental, so we need to be able to look at specific points and see whether anything is going wrong and press the emergency stop button, basically. So they're very useful, and we have a couple of them which get their power via PoE, which also makes things much easier for us, because we don't need to put a network cable and a power cable to the cameras. That's a very, very convenient function, definitely.
Yeah, for us it's a good side effect. Those equipments were designed for the railway industry, but obviously they find a good use here also in the mining environment, with shock, vibration, heat, dust, and having the reliability, redundancy schemes that are supported.
Exactly. Yeah, the requirements are very, very, very similar, because in both industries you don't want any component to fail. You always need redundancy, and even if you have redundancy, you still don't want any component to fail, because usually, like in the transportation industry, you have also high temperatures and closed cabinets. We have a bit of airflow here, which is good, but still, because we are in the desert near Las Vegas, we still expect high air temperatures. Like, we calculated with an air temperature of 50 degrees Celsius, which is quite a lot, because most electronics are only specified up to like 30, 35, 45 degrees. Then you have those industrial switches and media converters, which just work up to 75 degrees, which makes things much easier for us, because we don't need to implement any active cooling. We don't need to have any moving parts in the machine, or any more moving parts inside the machine. Less components that can fail.
Yeah, true. And I can see that you actually smartly designed the whole fixing in a way that the fins of the cooling, because it's all fanless, are showing to the backside, so that there is airflow possible.
Yes,
right?
exactly. So in the first attempt, the switches faced the other way, and this part here was closed. But then we thought, well, maybe it would be a good idea, because the air goes from the back to the front. Would be a good idea to cut this part of the sheet metal and turn the switches around, so they are in the direct direction of the airflow, to cool them down as good as possible.
Okay, Robin, thanks for having us here, for showing us around, showing us the Dirt Torpedo, the networking, the unique design of your torpedo plus the use cases, the challenges. That was very inspiring, I have to say.
Yeah, thank you for coming. Thank you for your time. We really appreciate it.
I think you still have a few weeks to go for the competition, is that right?
Yeah, we still have lots of stuff to finish, but we are on a very good way. In a couple of weeks, we will hopefully bore our 30-meter tunnel and not have it collapse.
So, up for the next couple of weeks, what would you say is the biggest challenge ahead of you?
Well, the biggest challenge ahead of us is figuring out how we travel into the USA, travel to Las Vegas, because currently, due to the COVID situation, there are still very strict restrictions for entering the USA. There is one way with a national interest exception, but it's very difficult to get. Maybe we'll have to go 14 days quarantine in Canada, something like that. But we're on it and hope to find a solution.
We certainly cross fingers for you.
Thank you.
And thanks again for having us, Robin.
Yeah, thank you for your time. And we would also like to thank all our other sponsors like the universities, DHBW Mosbach, all our other sponsors, and particularly Moxa, because on the network side, without you, we wouldn't be where we are now, because delivery situation, and you very, very helped us.
Was our pleasure.
Thank you.
Bye, Robin.
Bye.